Okay, let's start. So this is lecture 14, and we're going to be starting a new module, which are called pseudorandom generators. So today's class is going to be a very, it's just going to be an introduction of what these objects are. In some sense, this is probably, when people often think of pseudorandomness, these are the objects that people think of. But we did a few examples such as expanders and so on to get you used to a certain idea of what pseudorandomness means. And today we'll see a particular definition when it really comes to eliminating randomness from randomized algorithms, with that being the primary goal. In fact, in today's lecture, there's really going to be just one. I'm going to introduce a concept of what is called a hybrid argument, which will show up a lot in this in analysis involving pseudorandom generators, etc. It's possible that you've seen the hybrid argument or variations of this in other contexts, but it will be good to make sure that we are all on the same page and get comfortable with this particular thing. There's nothing too fancy about it, but we'll see one particular application of using what's called the hybrid argument. And then the setup for today's lecture, if I have time at the end, is to basically focus on a specific class that we will spend a lot of time on over the next few lectures, which will be related to reachability in graphs. And since graphs is something that we have been playing with for a bit. So let me start off by trying to formalize a notion of what do we really mean by a pseudorandom object. Okay, we were using this phrase a lot, but I want to say is that an object that exhibits some property that makes an observer think it was picked randomly. Okay, this is in some sense a very, very vague definition of what pseudorandomness means, but let's look at it from the context of examples we have seen so far. To me, one very, very nice example is the notion of expanders. When we dealt with expanders, we came up with one deterministic construction of an expander. So there's nothing random in that. It's a completely deterministic construction. But these graphs, if you pick any set, pair of subsets S and T, then the number of edges between S and T behave like as if these edges were thrown at random. Like in the sense that the number of edges that we had was roughly what you would expect it to be if these edges were thrown at random. So from that property, it was like, even though the particular graph you had in mind was a deterministic construction, it somehow has some sort of inherent properties that make it look like it was picked randomly. And the key point here is really, what the observer is. This is something that Prahlad had stressed in one of the earlier lectures, which is that, it's like randomness is in the eye of the beholder. So it's a question of, if you are working with a certain sort of an observer, can you fool the observer into believing that the object you're working with was picked at random? Okay, so a pseudorandom object is just a way of circumventing this thing of picking an object at random, but somehow it having enough properties in it that this particular observer believes that it behaves, it looks random. So in some sense, the observer behaves very, very similarly. Okay. So, and often what we might wonder is, instead of a pseudorandom object, maybe you're interested in a pseudorandom distribution. Okay. And by that, what we mean is, can we come up with a distribution such that with respect to a particular observer that we care about, the observer believes that this is completely, it looks random to that observer. Okay, so let's just look at a few examples to slowly internalize this this concept, which is, we saw this stupid 2 approximation algorithm for max cut, which was basically, we just said, let's take all the vertices, randomly color them with either red or black, and all the red vertices versus all the black vertices, whatever was the number of edges, we will say that's our, that's our estimate for the max cut. And we saw that this was a 2 approximation. Okay. But this particular algorithm was somehow expecting you to choose these vertices uniformly at random, like the colors uniformly at random. Okay. But we saw that, look, as far as this stupid algorithm is concerned, or as far as the analysis was concerned, had I fed it pairwise independent, distributions, the analysis would be completely unchanged. Okay, so in some sense, from the context of this specific algorithm or the specific analysis of this algorithm, pairwise independent happened to be a pseudorandom distribution. It's not really uniform, but it seems to have sufficient sort of complexity in it for this algorithm to not be able to distinguish whether I was getting a uniform distribution or a pairwise independent distribution, because somehow the analysis was looking 2 vertices at a time. So from that perspective, well, there's no difference between these 2 distributions. Okay. Now here is a contorted sort of example, but it will show up in many contexts, which is suppose your algorithm only did the following. There was some hidden set S, which the algorithm is not going to reveal to you. And the only thing it does is it takes an XOR of all those bits in that set S. Okay, it's a, you might wonder, why would you care about algorithms of this sort? Let's just just go with this for now. So now, obviously, if S was a non-empty set, this is going to be 1 with probability half and 0 with probability half. And one of the things we may want is like, okay, do I really need to feed it completely uniform bits to roughly get the same behavior? And we saw that there was this notion of what were called epsilon bias distributions. Which was pseudorandom for whatever algorithms or tests of this kind. If all that the algorithm is going to do is basically compute certain parities and do something based on that, well, you might as well feed it this as opposed to feeding it the uniform distribution. That's what we are trying to say. Okay. And then we saw other things, which was like, suppose your algorithm was something like it took a whole bunch of samples and then did some sort of empirical average. So it sampled, maybe you think of it as, you had a probabilistic algorithm which was making some error. You wanted to reduce the error. So you did this natural thing of running the algorithm on independent inputs and then sampling them. And taking the average of something of that sort. Okay. Again, the standard Chernoff would have said that, yeah, you need to take independent samples. But what we saw was that if you did an expander walk, then the different samples are not really like completely independent. They're all correlated in some way. But as far as this empirical average or some sort of sampling property is concerned, you don't really distinguish this from picking things uniformly at random. Okay, these were all various guises in which we saw this sort of general principle that, we are interested in looking for a particular deterministic or something that uses very few randomness to build an object that a particular test thinks is picked at random. So we are fighting against a test of a certain kind. We are not really trying to say that, I want to, I don't know how to say this differently, in the sense that I want to sort of say that, defining pseudorandomness depends on what you are fighting against. You are trying to fool a certain kind of a test or a certain kind of an algorithm or something. And you're trying to build something that works for that particular instance. Like just because expander walks work here, it's unclear if expander walks will work here. Okay. So it often you come up with constructions which are tailored on the particular application you have in mind. But sometimes there are these sort of nice, robust properties which just scale for multiple things. And to me, more importantly, it's the techniques that are more important. It tells you when you can use certain kinds of pseudorandom objects as opposed to others. But what we would really, really like is a pseudorandom object for the following kind. I have some randomized algorithm. And let's say I promise to you that this randomized algorithm runs in quadratic time. It doesn't take more than quadratic time. So for all I know, it could be using something like n squared random bits. Okay. Now, what I would really like is, can you come up with a pseudorandom distribution such that this randomized algorithm somehow believes it is being fed pure randomness, in the sense that its behavior is largely unchanged if that happens. Because if I could do that, then there is hope that I can just eliminate the use of randomness. I mean, instead of, the stupid enumeration algorithm was run over all possible random strings and just find out, did I accept more than 2/3 of the time or less than 1/3 of the time? But if I could do this more efficiently, that would be awesome. So what we really want is something here. And these sort of things are what I'll call pseudorandom generators. And today, we're going to slowly define this notion of pseudorandom generators and eventually instantiate it for a specific sort of class we have. Okay, so all of this will eventually boil down to the following definition of what is called computational indistinguishability. Okay, this is just a way of formalizing the fact that can a particular observer tell apart the two distributions x and y? Okay, and this is just a formalization of this. We will say two random variables x and y, which are both basically taking values on, say, m-bit strings. Okay, and let's say C is a certain class of tests you have in mind. It could be some bunch of functions. You could think of C as maybe taking an XOR of a certain subset of bits, or maybe this corresponds to a randomized algorithm, some sort of circuit or something that takes this as input and returns some real number between -1 and 1. Something, you have some notion of a test function. Okay, and the class of test functions that you're trying to fight against, I'm going to refer to as C. Okay, and we will say that two distributions x and y, which are supported on the same sample space, okay, are epsilon computationally indistinguishable for this specific class if the following property holds, which is, if you pick any test function from your class, its expected behavior on the distribution x must not really differ from the expected behavior on the distribution y. And I want the absolute value of this difference to be at most epsilon. Okay, so that is what we mean by computational indistinguishability. But in often cases, the C will happen to be like algorithm. In fact, the output will just be 0,1, and the class will just refer to things you can do efficiently. That's typically what C will be. But again, you can imagine that the definition might still make sense for maybe weaker Cs, maybe stronger Cs, etc. Okay, so this is just a way of saying that from the perspective of the class C, it can't really tell apart x from y. Its expected behavior on x is basically the same as the expected behavior on y. Okay, so
to recover, let's say I want to recover total variation from this.
So in that case, this will be the set of all possible functions from 0,1 to the m to the set 0,1.
I think just characteristic functions will also suffice, maybe, because total variation is the maximum.
Yeah, okay, actually characteristic functions will also, I mean, in the sense that what you mean, in fact, I mean, by characteristic function, you just mean you're going to choose a certain subset of 0,1 to the m, right? That's the same thing as saying it's a set of functions from 0,1 to the m to the set 0,1.
That's right.
Yeah, so if you take C to be the class of all Boolean functions, then this corresponds to indistinguishability in the total variation sense. Like they're statistically indistinguishable. But in many applications, that's too much to ask for. By the way, but hold that thought, because the next module we will see are what are called extractors, where what you're fighting against is statistical distance. Okay, so we will do that in the next module. But in this module, what I want to do is, like, many times you're not really fighting against all possible tests. You only care about tests that are efficient, because the class of functions you want to fool are efficient randomized algorithms, and you're trying to eliminate randomness there.
Yeah.
So it seems reasonable that, maybe it's easier to construct these computationally indistinguishable distributions in that sense. Yeah.
And this definition really has nothing to do with this 0, 1 to the m. One could just put any.
Yeah. So I just did this because we'll be dealing with randomized algorithms mainly.
Yeah.
And there, this will be the setup, which is the number of random bits your algorithm was using. And in fact, the range will just be 0, 1. I put range -1, 1 only for the sampler type of applications. Because if there is a particular function, like whatever, a potential or something you're trying to compute and you're taking an average, then maybe you're fighting against functions with this sort of range. But just ignore it. Most of the time, this will just be the set 0, 1.
Mm-hmm.
By the way, if it is the set 0, 1.
So can I just
comment?
Yeah. So this definition is very, very general. So we will see it in the context of, for the most part of the course, almost till the fair end, we'll only see it in the complexity point of view, the computation complexity point of view. And there will be, the set will be 0, 1 to the m. But then we'll see that these definitions are far, far more general than what they are. And we'll see it in completely different contexts. This will be the last few lectures. Hopefully we'll have time to do it. The notion of pseudorandomness is a much, much more general concept, and exactly what you said, that is, we will replace 0, 1 to the m with something else. We'll replace the structure of pseudorandomness. The definition will be exactly the same, but the underlying sets, the objects, the observers, everything will change. And based on this, it will be applied in different contexts. And we'll see this later. These are the topics which in the course, the proposed syllabus has things which we are going to do in outside the field of computation complexity. Those proofs will be along these lines. Yeah.
Okay. Thank you.
So just one thing I'd like to add is that if you think of the range as being 0, 1, this statement is the same thing as saying the probability that t of x equals 1 versus the probability that t of y equals 1 is roughly similar. Because the expectation is just going to be the right thing, right? So if it is just the range is a 0, 1, then you can replace expectations with what is the probability that t on the distribution x returns 1. And I want this to be roughly equal to the probability that t on the distribution y returns 1. Okay. So, this is just a formal way of saying something, which is that as far as tests from C are concerned, they roughly behave the same whether they are fed X or whether they are fed Y. Okay, and we are only talking about the average behavior. The average behavior of the tests when fed X is roughly the same as the average behavior of the test when it's fed Y. Okay, so just to instantiate it in a particular way, just imagine we had a way of starting with a randomized algorithm which had a certain error and reducing the amount of error. So what were we doing? We were looking at different samples, running the algorithm on each of them, and doing something like a majority, and figuring out what is the answer going to be. Now, what we saw in our expander construction, using expanders to reduce randomness, was that you don't really need these samples to be completely independent. Like if you had picked an expander random walk, that would have been good enough as far as this particular thing is concerned. Okay, and we were often saying this, so how many random bits did we use? We used a certain number of random bits and used those few random bits to actually generate a lot of samples. Because in order to generate a walk of length t, what did we do? We picked the first vertex and then we said, okay, we'll take the 7th edge, 4th edge, 42nd edge, etc., etc. So instead of picking m times t random bits, we just picked m plus order t random bits. So intuitively, there was some way of stretching a small number of random bits into a large number of random bits, which are correlated in some way. And that is what is going to be formalized by what is known as a pseudorandom generator. Okay, so a PRG, which is just short for pseudorandom generator, for a class C, just refers to the following thing. Okay, it's some map that stretches d bits into m bits. Okay, and the intuition is that instead of feeding m random bits, what I'm going to be doing is picking d bits uniformly at random and just apply the function g on it. So think of something like a map of the form u, I1, I2, till IT going to U1, sorry, U equal to U1, U2, U3, UT plus 1. This is sort of what we had done in expander random works. We would pick the first vertex at random and then pick edge labels uniformly at random. And just say when you want even if you want T plus 1 samples, well, here is the T plus 1 samples. It corresponds to a random walk. So this is sort of the map that we have in mind. That's what I'm going to call G. Okay, so a map G is said to be an epsilon pseudorandom generator if the output of G on the uniform distribution is sort of computationally indistinguishable from the uniform distribution. Okay, that's all we are saying. We are basically saying that a pseudorandom generator is just a function such that it gives you a way of stretching D uniformly random bits into M correlated random bits, but in a way that a small, like a test from your class is it cannot distinguish the two distributions. From the test perspective, they look the same. Okay, and again, just to stress, in often cases, in almost throughout the thing, the class C corresponds to I don't know, something like size M squared circuits or something. Okay, so something like that. You pick up some mental model of efficient computation and you'll work with it. And sometimes we'll actually work with or some subclasses. Some subclasses of, I don't know, our mental model of efficient computation. Okay. And in such settings, if you are working against circuits of size S, sometimes people write it as S comma epsilon pseudorandom generator to just mean that you're fighting against circuits of a certain size, circuits of size S or something. But okay, anyway, we'll deal with it when we get there. But hopefully, intuitively, the definition makes sense. Okay, it's just things that we have seen so far, and we're just writing it in a certain language so that we can talk about it in a little more general. Okay, now, so again, the point is, I mean, you're not fighting against algorithm that runs in just, that only runs on some M inputs. Because algorithms, the input lengths could be vary, right? And so often, I mean, this is something I'm going to continue to keep skirting, which is that, you're really dealing with a family of such functions. That is, if you're trying to fight against a circuit that works on M inputs, there is a generator that corresponds to that, which maybe is stretching dm bits to n bits. Okay, d of m bits. D of m could be some function. Think of d of m as, I don't know, root m or log m, log m, something. There's some way of stretching a small number of bits to a large number of bits, such that the class that you're interested in is fooled into thinking that the output was truly uniform, when it's actually not uniform. Okay, so what are the things that we would want from such a generator? Ideally, we would like this D to be as small as possible, because we were constantly saying that I want to reduce the amount of random bits used. Okay, I don't want to be able to use a lot of random bits. And the other thing also, that I don't want this computation of taking D bits and stretching it to M bits. I don't want this computation itself to be very expensive. Okay, those are two things that we would like from such a generator. Okay, and just to concretize why these are things that we would want, let's just look at oh, by the way, let me just give a definition, because I need to now specify what does it mean to say this is efficiently computable. It just means that there is some algorithm M, which when fed 1 power M and X, by 1 power M, I just mean it's a string of length M, and X, it returns the value of GM on X. And maybe you want to know what is the seed length. So this D of M is called the seed length of the generator. If you want to know what the seed length is, okay, this maybe the same algorithm gives you the seed length as well. Okay, and we'll say that this generator is T of M computable. Maybe T of M is like M squared, like 2 to the M, whatever, depending on what your computation, how efficient the generator computation is. To just mean that, these evaluations are some things that you can do in time. It's just a very natural what you would expect to be. When you say that I want the generator to be efficiently computable, as a function, I want it to be efficiently computable, which means there is some algorithm that does this computation for it. Okay. Now let's just see one concrete example as to why are we.
So notice when you're defining TM computable, this is slightly different from the usual notion of this one. Usually when you say something is T of some computable, it's based on the input length of the object. And here you're not basing it on the input length, but rather on the output length. And Ramprasad, if you comment on that, why here we.
Yeah, so maybe once we see the proof of it, we will see why that ends up getting used. But I think another point to keep in mind, I'm glad Prahlad raised this, which is that often you're thinking of generators that start with a few random bits and generate a lot of random bits. So you would ideally want to say that, it's not fair to sort of say that I want a generator that runs in polynomial time and just DM, because maybe it is trying to output far too many random. So in fact, that's the sort of setup we'll be trying to work with. You would really hope for DM to be something like log n. Okay. So we are going to try and say that, I am okay as long as you take polynomial in the output length. But once we see the proof, we will see exactly where we need it. Okay. Once we see the proof of this theorem. And Prahlad, at that point, if I have not made the point you're thinking of, please, yeah. Okay. Okay. So here is all we are trying to say. If we are saying that if there is a generator that stretches DM bits to M bits, okay, for, whatever, against circuits of size, I don't know, size at most M or something, then it automatically tells you that you can de-randomize any randomized in some form, okay? And how bad will your de-randomization be? Well, it depends on how small D of M is. So it's going to be 2 to the, something like 2 to the D of poly N. And there is some other factor which corresponds to how efficient this generator is. Okay. Even before we see the proof, this should intuitively make sense to you. So the stupid de-randomization of any randomized algorithm was just, let's run over all possible random strings and just run the randomized algorithm on all of them and figure out, did I end up accepting more than 2/3 of the time or less than 1/3 of the time? Now, intuitively, if you have a generator of this sort, you don't need to run over all possible M length random strings. You only need to run over all possible D of M length random strings, roughly. Right? So it makes sense that there is some 2 power D sort of factor that comes. This really comes because, now for every such random string, you may have to run your original algorithm and also compute what is G of that particular random, G of that seed. So hopefully this makes sense. The proof of it is just formalizing, like figuring out where this N power C, etc. comes from, etc. But this theorem should not be surprising to you at all. So I hope that's okay. Okay. So let's just see a quick proof of this. So let's just say that A is a randomized algorithm running in time at most, something like, let's say, N to the C, and I'm going to refer to this as N. Okay, which means that A uses at most M random bits. Now, suppose I give you an input X, and I want to know, does, is X in the language L that A is trying to solve or not? So what do I want to know? Notice that if X is in L, this implies that the probability that A accepts, this is at least 2/3. And if X was not in L, then the probability that A of X, R equals 1, this is at most 1/3. This is just a definition of what it means for a certain language to be in B, that it can be solved by a randomized algorithm. Now, okay, so now what are we going to do? I'm going to now define a new algorithm. Okay, B, and this B, again, it has input X. Okay, so this is what B is going to do. So the first step is B is going to build a circuit T from, I'm going to think of it as 0, 1 to the M to 0, 1, such that the job of T of R is basically to just run A of X, R. Now, I mean, I think there was a short discussion on Academy sometime, long time back, which is that if you have a description of the algorithm A, then building the circuit is actually very easy. I mean, there's a standard nice way of building it. And the size of the circuit is also something. And let's say, I'm just, again, it's like cheating and say that, let's say the size of the circuit is also M. Just choose M to be whatever is the larger of these things. Okay. And now what we do is the following. We basically just run over all Y in 0, 1 to the D of M. Okay, compute Z, which is equal to G of Y, and count the number of such Y's such that basically A of Z equals 1. Okay, and now you basically accept if this number is at least, I don't know, half times 2 power D. Okay, so that's the algorithm. It's basically it's just this, I mean, it's what you expect. I mean, run over all possible Y's, which are all possible seeds to the PRG, compute, I mean, G on that seed. So it will give you some M length random, I mean, like pseudorandom string. Run A on that pseudorandom string instead, and count how many of them result in A of Z equal to 1. Okay, now notice that if A on uniformly random strings was taking, I mean, it was equal to 1 with probability 2/3. And if I start off with a generator, I don't know, what did I choose that to be? I start off with a generator that is 1/8 pseudorandom. I mean, it's still going to be at least as large as 2/3 minus 1/8. And 2/3 minus 1/8 is still at least half. Okay, and that's all that we are saying. We are saying that, you know, the original acceptance probability was 2/3. By the acceptance probability on the pseudorandom generator will have to be at least as large as 2/3 minus 1/8, because it has to be within 1/8 of whatever was the old value. Okay, so this basically tells us that, I mean, PRG guarantee implies that B is correct. Okay, and that completes the proof. Hopefully nothing here is really surprising to any of you. I mean, it's basically we are doing this enumeration. Instead of doing the enumeration on the entire length, I mean, M length random string, we are doing the enumeration on the C. That's it. So are there any questions right now? Okay, good. So hopefully now it therefore tells you that this is the reason why I would like this to be small and I would like this to be small. And if these two are small, we are in pretty good shape. Okay. But by the way, this also tells you something more, which is that if this is the application you have in mind, why do I really care about T of n to the C to look like poly in n to the C? Suppose instead I had told you that T of n to the C was something like 2 power D of n to the C. Nothing really changes here, right? Because I'm anyway paying a factor of 2 power D outside. If T also takes 2 power D time, I mean, like, that's good enough for me. Okay, so this is why pseudorandom generators often there's two descriptions. We will say a generator is mildly explicit if the running time happens to be poly in M and 2 power D, versus fully explicit, which is like, I just want it to be poly in M. I am not going to allow you to run in time 2 to the D of M. And hopefully this reminds you of something very similar to our definition of expander graphs, where mildly explicit is like saying that you're asking it to output the whole truth table in poly time. And the truth table itself is of length 2 power D times M. So I'm letting you run in polynomial time in the truth table length. Whereas this is like saying, I don't care about the entire truth table. I care about what is the value of the generator on this seed. Like computing G on a specific seed. So hopefully this reminds you of what the two definitions we had for expanders. One was we were saying that expanders, there was one way in which we wanted to say, I want you to write down the adjacency matrix of this graph completely in polynomial time. That was one ask. The stronger ask was basically saying, I don't care about the entire adjacency matrix. I will give you a vertex. I will tell you I want the 7th neighbor. Can you do that in polynomial time in the input provided to you? So it's analogous to the definitions we had seen. Okay. So Prahlad, is this the point you wanted to make?
Yes.
Okay, good. So this is the definition of fully explicit versus mildly explicit. But I guess at this point, we will take anything that we get because we are really looking for pseudorandom generators that are non-trivial or something. So let's first ask the most basic question, which is—
And also the point that if you just want to de-randomize BPP, mildly explicit is more.
Yeah, so from the above theorem statement, if you had a mildly explicit thing, you will still end up with 2 power d of m times poly n. That's the de-randomization you're going to end up getting. I mean, irrespective of whether t is like poly m or not. I mean, even if t was like 2 to the order d of m, you're basically going to get the same thing. Okay, that's why for this particular application, maybe mildly explicit is good enough. But again, you might imagine other applications where you want strongly explicit. Okay. So now let's ask the most basic questions. Like we are saying that, this particular object is super useful. It allows us to get rid of randomness, etc., etc. But why do these things even exist? Why do we expect them to be there for them to be functions that stretch d bits into m bits that is supposed to somehow fool all randomized algorithms? Why should that even be there? And whenever you're dealing with pseudorandom objects, it's always good to basically ask, you first check if a random object works. Okay, so that's what we are going to do. So whenever there's, it's like, this is what we did in expanders also. Before we built expanders, the first thing we did was, if I pick the graph at random, does it have the property I am asking for? And we're going to do something similar here. We are just basically going to say, suppose I pick this function at random. Okay, does it have the property of fooling circuits of a certain size? I don't know, let's say m length circuits. And the theorem that we are going to see, it's going to, hopefully you'll see this style of proof so often that this will just become second nature to you. So we'll show that, there do exist pseudorandom generators where d is roughly like this, like log m plus log 1 over epsilon. Okay, so at least this will hopefully show existence. Okay, in fact, not just that there are pseudorandom generators, this should actually be there are lots of. That is, if you pick a function g at random, with very, very high probability, it will be a pseudorandom generator. Okay, so here's what I'm going to do. We'll pick this g from 0, 1 to the d to 0, 1 to the m uniformly at random. So once I picked a g, I now want to ask, now what are the chances that this actually works for circuits of size n? That is, no circuit of size n can really distinguish between them. Okay, now suppose we fix a circuit. Okay, T of size n. Okay, now let's ask ourselves, what is the expected value of T on G of y? What can we say about this? What is this exactly? So notice that once you fix what is G going to do for every input that it's provided? It is just going to spit out a random element in 0, 1, 2, 3. Okay, so this is basically going to be 1 over 2 to the D times, what should I, some P of, let me use Zi here. I going from 1 to 2 to the D. Because, it's an average of whatever strings y. There are 2 power d such strings y. And this is that average. And if G is picked at random, what you're really doing is taking an empirical average, because this G was picked at random. So each of these Zi's are random. Okay. So each Zi is taken from uniform, but because I fixed a G, these Zi's are now fixed. Now, this basically looks like Chernoff bound, right? The actual expectation, mu, this is basically expectation of T on the uniform distribution. This is some mu. But once I fix a random G, it's like saying that I will basically sample it at, some 2 power D points and take its average. So, I'm hand waving a little bit, but hopefully this makes sense, which is that Chernoff basically says, you are within some parameter epsilon with probability at least something like 1 minus exponential in some epsilon squared times number of samples. Number of samples here is 2 to the T. Oh, maybe I forgot a minus. Yeah. Okay. There's some constants, etc. there, which I'm just ignoring. Okay. So what does it mean to say this generator, or rather this purported generator, is not actually a pseudorandom generator? It means that one of these deviations is just way too large. So if G is not a PRG, then what is this saying? This is just saying that there exists some circuit T such that the expected value of G of X, G of the uniform distribution, minus 1 over 2 to the D times summation, sorry, why did it become G? What I meant to say was T of U times T of Zi, I going from 1 through D. This difference is at least epsilon. Now let's ask ourselves, what is the probability that this actually happens? This probability is over the choice of G. I'm picking a G at random and then asking, what are the chances that there exists a circuit such that this deviation is too large? For every fixed circuit, the deviation is large with probability only this much. It's a fairly small probability. Okay, so this is at most the number of circuits times, I don't know, something like exponential in minus epsilon squared times 2 to the D. This is just going to, just by the union bound, this is going to be the number of circuits of size. I don't know what we were fighting against. We are fighting against circuits of size M. So circuits of size M. So the number of circuits times this much. Okay. So in order to get a good bound on this, you just need to figure out what is a reasonable bound on the number of circuits of size M. And it's this is something I'm not going to do. So it's easy to see that this is roughly like 2 to the order M log M. Because in order to build a circuit, for each gate, you need to tell who the 2 inputs are and what sort of gate you are. And if you just work out, you get something like 2 to the order M log M. So what does this mean? So this means, so therefore, if this D is chosen such that 2 power D times epsilon squared is bigger than, is bigger than M log M, or let's say some, I don't know, some large constant times m log n. I don't know what this constant is. I'm just putting 100 to be safe. Okay. Then this, the whatever the inverse exponential quantity is going to dominate. It's going to completely squash whatever value you might put there. And for this to happen, so this implies d equals order log m plus log 1 over epsilon is sufficient. Okay, so that tells you that if the seed length was at least as large as, I don't know, some 100 times log m plus log 1 over epsilon, this is certainly going to be true, which means this quantity is really, really close to 0. It's very far away from 1. So which means with very, very high probability, the G that you ended up picking is actually a pseudorandom generator. Okay, so this was a really quick sort of calculation, but hopefully this was clear to you. And like is often in the case of the pseudorandom objects at all, we almost are always in this question of, can we find hay in a haystack? By which what I mean is, we are looking for a pseudorandom generator. We would really, really like to get our hands on a pseudorandom generator. And then there is always a theorem that says, if you pick a generator at random, it's a pseudorandom generator, which basically means there are plenty of pseudorandom generators. Okay. And we are struggling to just find one explicit construction. And this was also the setting in expander graphs. We knew expander graphs were in plenty because you pick a graph at random, it has all the expansion properties. But then we had to struggle to actually explicitly get our hands on an expander. And this will turn out to be the same for, if you're dealing with error correcting codes. If you pick a bunch of strings at random, with very high probability, it will be an excellent code. But again, you are struggling to somehow get our hands on. So all of this fall in this category of, finding hay in a haystack, so to speak. Okay. But the sort of trying it on a random setup is very useful because it tells you what are the aspirational parameters that you should try to achieve. So it tells, since a random construction works with seed length being this, you should mentally tell yourself, oh, okay, that's what I'm trying to get. So an aspirational goal could be that I want to find an explicit PRG, the fact that this explicit is important, that tries to have the seed length that a random object is, because that's your gold standard. You're trying to somehow achieve something like that. Similar to the fact that we wanted to get graphs, we wanted to get expander graphs, and we said that random graphs achieve a certain threshold. We call that Ramanujan. And then we said, okay, can we get Ramanujan graphs? That's what we are trying to get. Okay. But to be honest, I mean, at the moment, we will take anything. Basically, I mean, if you give me a D, which is little o of M, I will be super, super happy. I mean, it's like whole beggars choosers sort of situation. I mean, at this point, we have nothing here. So, I mean, give me anything non-trivial. I'm not really going to force you to give me an order log m. Yeah, that is aspirational. But at the moment, let's just make some progress and then figure out. So, okay. So is the discussion okay so far? I hope the definition of pseudorandomness, the context of pseudorandomness when it comes to de-randomization, these things are clear. If there are any questions, I mean, please feel free to ask. Okay, so what we are going to do next is to get a sense of how do you end up trying to construct these PRGs. This is what we are going to be spending the next few lectures on. But let's start today and see how far we get to, and then we'll see from there on, which is, let's ask for a slightly simpler requirement. So a pseudorandom generator was a way of saying that I want all my m bits to look uniform. Let's ask a weaker requirement, which is what is called next bit unpredictability, which is, we will say that a distribution, again on m length strings, okay, is set to be t comma epsilon next bit unpredictable if the following happens. That is, no matter what circuit you pick up of size t, it can't guess the next bit with significant advantage. Okay, so this is just like saying, given a prefix, guessing the next bit is hard. So formally speaking, that is, there should be no small circuit P and an index I, such that when P is fed the prefix x1 through xi minus 1, that is, you pick an x at random. Like you pick all the m bits uniform, like according to the distribution x, but you only give it the first I minus 1 bits to this circuit P. And you ask P to figure out, can you now tell me what the next bit in my sequence was supposed to be? If P is able to do that with significant advantage, then this is actually next bit predictable, because I'm able to do it better than random guessing. One stupid way is like P will just give up and say, I'm just going to pick a random. But that is like trivial. So I want to say, can you do better than that by some parameter epsilon? If you can do that, we will say that this is next bit unpredictable. Okay, so I hope the definition of this is clear. To me, it should feel to you like, this is certainly a simpler simpler ask than saying that this P should not be able to differentiate this from the uniform distribution. So hopefully constructing next bit unpredictable distributions are a little easier. So, but the nice lemma is that turns out these two are equivalent statements if you're willing to lose a little bit on parameters. So it turns out that a distribution is T comma epsilon pseudorandom, by which I just mean it is epsilon pseudorandom against circuits of size P. Okay, it's just shorthand for that. Turns out that it is T comma epsilon pseudorandom. If it is T comma epsilon pseudorandom, then it is basically T comma epsilon next bit unpredictable. That hopefully should not be a surprise. But perhaps the more interesting situation is if you actually have a next bit unpredictable distribution, then it is indeed a pseudorandom distribution. If you can't predict the next bit, in fact, it looks the entire sequence should look random.
Okay. So we have specialized to the case where x was a uniform random variable and all these.
No. This is just some arbitrary random variable on 0, 1 to the n.
Okay.
So if it is a uniform random variable, I really can't do anything better than half. Right? But we are saying that let x be any distribution. Okay, pick up any distribution that you want, but just think of it, it's a distribution on 0, 1 to the n, so I can think of it as bit by bit, so to speak. And we're just saying, if I give you a prefix, are you able to make an educated guess on what the next bit is going to be? If you can do that with significant advantage, turns out this is an if and only if of whether the sequence is pseudorandom or not. Okay, good. So hopefully this should be very, very believable to you. The other direction may feel like it requires a bit more work.
So, in the theorem where you showed there are plentiful PRGs. Did you take x to be uniform there?
Sorry, which is x here?
T of u, right? So
T of u is what this is the ideal situation. That is, this is T's behavior on the truly uniform distribution. But we want to say that T's behavior on this must look roughly the same. So here y is chosen according to the uniform distribution, but it's according to the uniform distribution on just D bits. Is that okay?
Okay.
Yeah, so we are basically saying that T had a behavior on if I pick this M length string at random, but we are basically saying suppose I picked up just the D length string at random, applied this function to get an M length string. There are obviously correlations here. Does T still behave the same? That's what we were trying to show.
But a PRG should be closed for any distribution, right? Like X or Y, like that was your earlier definition, right?
The PRG should be closed against any test you mean, right? When we define a PRG, all we are saying is we are fighting against the uniform distribution. So we are basically saying that this is a PRG if the output of the generator on the uniform distribution looks like the uniform distribution on M length strings for the test that you care.
Okay.
Yeah. Yeah. Okay. Good. Let's quickly go over what we are doing here, which is that we are trying to somehow show that being pseudorandom and being next bit unpredictable are roughly the same things. Okay. Now, so let's just see the proof of the forward direction, which should be the more natural thing. So let's say X was pseudorandom. But not next bit predictable. Sorry, let me just say, but next bit unpredictable. What do I say? I want to say it is not next bit unpredictable, so it is next bit predictable. What does this mean by definition? This means that there is a circuit P.
You're proving the contrapositive, no?
Uh,
That's all you're going to prove. You're showing it's which next bit predictable, it's not pseudorandom.
yeah. Okay.
By all of.
Yeah, okay, fine. Well, whatever. I'll just write down what I was trying to say. Okay, there's a circuit P of size at most T or whatever, and an index I, such that if this circuit is fed a prefix, this ends up returning xi with probability at least half plus epsilon. Okay. Now, how do I use this circuit to build a distinguisher from the distribution X and the uniform distribution? What's the most natural thing you will try? So I'm given X1 through Xm, and I'm trying to figure out, did this X1 through Xm come from the uniform distribution, or did it come from this pseudorandom distribution X?
Running this multiple times will sort of be a very good chance of guessing.
In fact, you don't even need to run it multiple times. Let's just run it once. So I'm going to define a new algorithm, okay, which on input X1 through Xn. I mean, okay, maybe I shouldn't say X1 through Xn. I'm going to get as input, I don't know, some Z1 through Zn. I have no idea if Z is coming from the uniform distribution or Z is coming from the distribution X. Okay, I'm just going to say except if Zi equals P of Z1 through Zi minus 1. That's what this algorithm is going to do. Okay. So now, let's call this algorithm as Q maybe. Now, what can I say about the expected behavior of Q if I fed it the uniform distribution on n bits? Oh, at some point I went to n versus m, is it? I guess this should have been m. So what should this be? I mean, the chance of this next bit is, I mean, if it was uniform, this next bit is going to be completely unrelated to Z1 through Z, the previous things. So the chance that this equality actually holds is just half. So this is just going to be half. Okay. But what can I say about the expected behavior of Q on whatever, on X? I don't know why this became square brackets. Now notice, if this Z1 through Zm was actually distributed according to X, then this P was supposed to get it right with probability at least half plus epsilon. So the chance of this Q accepting is going to be at least half plus epsilon. Okay, but then these two, they differ by, I mean, the expected behavior seem to differ by epsilon. And that's a contradiction to the fact that X was pseudorandom, or if I had not assumed this, then this is like saying that X is certainly not pseudorandom, because you just built a distinguisher. that seems to be able to tell apart the distribution X from the uniform distribution. I mean, at least the difference is at least epsilon. Okay, the T minus order 1 comes only from the fact that the description of this circuit is a little larger than the description of T because you're doing one extra equality check or something. So, okay, so that's all this is. So is this okay so far? So this part is the more natural, the easy direction. The other direction is the more fun direction. So that is, how do I go from a distribution that just happens to be next bit unpredictable and somehow show that it is, it looks like a uniform distribution. Okay, so we have only given that X is, I don't know, T comma epsilon next bit unpredictable. Want to show that X is sort of computationally indistinguishable with maybe a gap of like epsilon m or something from the uniform distribution on members. Okay, and the way we are going to do this is using what is called a hybrid argument. Okay, I mean, it might, I mean, in fact, it's just it's basically just triangle inequality in some sense, but it's a sort of powerful tool. Like once this becomes something that is you're comfortable with, I mean, there are numerous contexts where this show up. And in fact, the hybrid argument, I mean, it's like saying that, oh, pigeonhole principle is an extremely simple statement, but you can use pigeonhole principle to prove really, really cool things. I mean, it's like you need to find out what the pigeons are and what the holes are. And similarly, the hybrid argument also, on the face of it, it's a very, very simple argument, but it's the way in which you use it. And hopefully in the course of these next few lectures, you will see many, many applications of the hybrid argument.
Isn't it hybrid walk argument? Or...
Oh, I thought it was just, I've somehow never heard the phrase hybrid walk argument.
No, it is, at least by the people who came up with it in the CS world, it's called hybrid walk argument.
Oh, is it? Oh, I had no clue. Okay.
And I'll tell you why hybrid walk when you finish that.
Okay. So the idea is basically it's basically what you do is you're trying to somehow show that a distribution that looks like X, like full of all made up of these X's is similar to a distribution that is made up of uniform, like coordinate by coordinate in some sense. And rather than make a big jump, okay, maybe that's what you mean. Okay. Rather than making a big jump from the gap between these two, you try to take walks, you try to take small steps and show that in each of these steps, you're not really changing by much. Well, if that were the case, then this and this can't be too far apart. That's the rough intuition. Okay. And so this in general is what is called a hybrid walk argument. I now see why walk makes sense. Okay. But let's just fix some notation. Let's say that we'll just call distributions y0, y1, y2 all the way till ym, where in general, yi refers to the fact that the first I coordinates are xi's, and after that you just fill them with uniformly random bits. Okay, so ym means that the first m coordinates are xi's, which is the same thing as saying it's the distribution x. So ym minus 1 is like the first m minus 1 of them are x's, then you put a uniformly random. And similarly, on y0 is basically none of them are x's, but everything is filled with a uniform distribution. So is the definition clear? Okay. So now what is the aim? The aim is now going to instead, we'll show that this x, which happens to be equal to ym, is basically computationally indistinguishable to ym minus 1. Which happens to be computationally indistinguishable to ym minus 2, such that then eventually you reach ym. And all of them are going to have an epsilon Okay, and this together will imply that X is computationally indistinguishable with respect to M epsilon from the uniform distribution. Okay, so why is this true? Well, suppose it was the case that it was not computationally indistinguishable. What does that mean? So this implies that there is a P, okay, such that this holds. The expected value of P of y0 minus the expected value of P of ym, this is at least epsilon. Okay, and this is just triangle inequality, which is that you just write it as M going from, what do I need
It's
to
an
write?
M epsilon, I think.
Sorry?
That should be an M epsilon.
Oh,
because-
sorry. Yeah, this should be an M epsilon. That's right. Thank you. Okay, this is like M epsilon. So this is like I M going, okay, M going from 1 to, this is a bad, I going from 1 through M of expected value of P of y, what do I want to put? Yi minus 1 minus expected value of P of yi. This is at least M epsilon. It's just triangle inequality. I'm writing this as P of y0 minus P of y1 plus P of y1 minus P of y2, and just telescoping the whole thing and just breaking it up into just using triangle inequality. Okay. So now if a sum of M things is bigger than M epsilon, then it better be the case that one of them is bigger than epsilon. I mean, at least one of them is bigger than epsilon, which implies that there exists an I such that expected value of P of yi minus 1 minus expected value of P of yi, this is at least epsilon. Okay. Now, here's one small trick. Since if you want this to be true, where the difference is at least M epsilon, if you replace P by not P, just note that the sign of the thing inside is going to swap. Right? Because, I mean, whenever it was outputting 1, it's outputting 0, it's outputting 0, it's outputting 1. So I'm just going to hand wave a little bit and say that you might as well assume that there are no absolute values. Like you start off with a circuit such that P accepts y0 more frequently than it accepts ym. And now you are saying there must be some I such that it accepts yi more frequently than it accepts, sorry, yi minus 1 more frequently than it accepts yi. Okay, so this is just, let me just say, by replacing P by not P if necessary, no absolute values. Okay, so now basically this is what we are trying to contradict now. We were told that something is next bit unpredictable, and now I am also told that the way it behaves on a distribution, I don't know, oh, I must have written, the way it behaves on a distribution yi minus 1 seems to be different from the way it behaves on the distribution yi. And this feels like, it's like, like what else can you do besides predicting xn? So that's what we are trying to get to. Okay, so let's just note this, that P is more likely to accept yi minus 1 than yi. Okay. Now, okay, so now I need to build a distinguisher. I mean, I need to build a next bit predictor to somehow contradict the fact that we assume that it was next bit unpredictable. Okay, so what are we going to do? So I'm going to define a circuit P tilde, which gets input x1 through xi minus 1. and somehow I'm trying to predict what the next bit should. So what is a natural thing that you can do at this point? What is a good way to predict the next bit? Any thoughts?
I mean, I would like to say that just pick these remaining bits at random and then feed it that, but then that's an extra randomness which I did not want.
That is fine, but let's assume that, right now, let's first build a randomized circuit, and eventually there'll be some way of fixing random bits, etc. that will work out. But let's say for now we can freely choose more random bits if necessary. Okay, so but yeah, that's a great this thing. So let's basically pick let's say zi plus 1 through zm at random. Okay, and let's just compute what does p do when I feed it x1 through xi minus 1, zi through zm. Okay, now suppose p returns 0.
So
What should I do?
Zi also at random?
Sorry?
Are you picking Zi also at random?
Oh, sorry, I wrote zi plus 1 here. What I meant was zi. I mean, zi onwards. Pick all the other bits at random. And I'm basically going to just ask, what did p do on this string? Okay, maybe p accepted, maybe p rejected, I don't know. But I want to somehow use this to now output an educated guess for what xi is. So what is a reasonable thing to do? So the key point is that p is more likely to accept a uniform distribution than the distribution coming from xi. Okay, so mentally it feels like suppose p ends up accepting, it's more likely that this xi is not, or rather it's more likely that the zi is not the xi I'm looking for. Because had this actually been xi, I feel like I'm a little less likely to accept. So what I'm going to do is just the following thing. I'm just going to say if b equal to 1, return zi bar, else return zi. Or in other words, basically return b XOR xi. Sorry, zi. Okay.
In fact, I thought what you wrote before was you pick zi plus 1 and instead of at zi you give 0 or 1. You deterministically give 0 or 1 to figure out which one to output. Because right now you are giving it the distribution yi, no? The unadulterated distribution yi.
Sorry, what?
I thought what you will be doing is, this also works, but I think the simpler one also works. That is just pick zi plus 1 to zm at random. And then
try out both of them.
Find out whichever one it gives more and give it output that way.
What do you mean by whichever one it gives more?
So whichever one it accepts.
What if it accepts both or rejects both?
Then you toss a coin in this one.
Yeah, so that part is what I'm like, I somehow don't like that analysis thing.
Okay,
let's just see. I mean, like, so this I don't know, to me this felt very natural, but you can also do exactly what Prahlad is suggesting. Okay, just try out both choices for xi and figure out which is the better thing to accept. If you don't have much information on which is the better thing to accept, just toss a coin and decide. Okay, so we need to get a sense of what is the probability that this p tilde is correct. Okay.
No, I agree. The analysis is just going to go through. The point is, at least intuitively, right now, the distribution you have fed it is the distribution yi.
I have fed yi minus 1.
Sorry, yi minus 1.
Yeah, that's right.
Okay, go ahead.
Yeah. Okay. So now let's get a sense of what is the probability that pi is. Okay. So now, okay, I'm going to define two quantities. Let alpha be the probability that when I feed p x1 through xi minus 1 followed by xi and then uniform distribution. Okay, that this accepts. Okay, I'm going to call this alpha. This is basically what is p's behavior on the distribution yi. That's what alpha is. And it will be convenient to also look at the following thing. The probability that I feed x1 through xi minus 1, but I just flip the ith bit. And after that, I feed the uniform distribution. Okay. Now, given these two, what can you say about the probability that P accepts x1 through xi minus 1, ui plus 1, um? Now, with probability half, I would be in this situation. With probability half, I will be in this situation. Because whatever this ui is, either it equals the correct xi, or it does not equal the correct xi. So this is going to be exactly half of epsilon plus epsilon, sorry, half of alpha plus alpha prime. Is this clear? Okay, I'm hoping it's okay. So this basically is going to be half of alpha plus alpha prime. And I know for a fact that this has to be at least as large as this plus an epsilon. Okay, so this tells me that this is at least alpha plus epsilon. Okay, and together this should imply that alpha prime is at least alpha plus 2 epsilon. I mean, just rearranging things. I mean, I know that this is at least this, so just rearrange it and you get a quantity of this. Okay, now let's ask ourselves, what is the probability that P tilde is correct? Okay, when will P tilde be correct? So there are two cases where it is correct, which is that the Zi that was fed was equal to Xi, and this B happens to be equal to 0. In which case you will return the right thing. Or the Zi that was fed was equal to not Xi, and you returned a 1. Then you will sort of negate it again and you will return the right value. Okay, so P is correct if Zi equal to Xi and B equal to 0, or Zi equal to Xi bar and B equal to 1. Both of these cases happens with probability half because I picked Zi uniformly at random. Right? So therefore, this is just going to be, so the probability that this guy accepts, it's half. Suppose it was the case that Zi equal to Xi. What is the probability of me outputting 0? Well, the probability of me outputting 1 was alpha. So this has to be 1 minus alpha. Now the next thing is, like, if Zi is equal to Xi bar, the probability of me outputting a 1 is exactly alpha prime. Okay, so this is just going to be half plus half into alpha prime minus alpha, which we know is at least 2 epsilon. This means this is at least half plus epsilon. So we have just found a distinguisher. So what we built here was actually a distinguisher that is able to distinguish, we built a next bit predictor. It's somehow able to predict the next bit with advantage epsilon normal. And that basically completes the proof. Was this okay? I mean, hopefully it's not too fast or anything. Yeah, if this part is unclear, please interrupt and ask questions. So this is the last proof I really wanted to give. The next is just going to be an exposition of what is going to happen from this point onwards. So what we have now shown is that if you ignore the, this epsilon versus m epsilon, I mean, if you ignore exactly what the parameters are, then getting a next bit unpredictable distribution is equivalent to getting a pseudorandom distribution. Okay, so you might as well work with next bit unpredictability if that is easier for you to construct. Just come up with some way in which you can just prevent the next bit from being predictable, and hopefully And that, I mean, this lemma basically tells you that that's already good enough for you to get pseudorandom distributions. You might have some loss of parameters, but let's ignore that for now. Okay. So yeah, so this is it's a fairly simple proof. It's just getting used to taking one circuit, slightly modifying its output to get a different circuit, etc. And so that's all I wanted to say here. Now, one possibility is to sort of maybe. Yeah.
No. So I want to just, this is a complete aside. Why it's called hybrid walk and stuff. What I would have made Ramprasad do if he had been an actual physical class. This is the way Silvio Micali taught. When I was first taught the hybrid walk argument, he came to class and tried to jump from one end of the class to the other end of the class in 10 steps and said that it's a long distance. At least one of the steps should be, he should have jumped a long distance. And
okay.
This is how a hybrid walk. By the way, so in the theoretical computer science literature, the hybrid walk argument is it's just triangle inequality. There's nothing more than triangle inequality. But on the other hand, realizing that it's useful, I think happened due to in a paper of Goldwasser and Shafi Goldwasser and Silvio Micali while trying to define probabilistic encryption.
Yeah.
That was the first paper. But by the way, seems as if it's a fancy name to give to this one. The probabilists also do this. They call this the Lindbergh technique. So in multiple fields, it's called this sort of taking n steps and realizing that if the sum of the n steps is large, then one of the steps must be large, is a very powerful thing that is used. Yeah.
Okay. For once, I'm glad that this lecture is not a physical thing, so that I could, Prahlad wouldn't have forced me to do this jump thing. Okay, so let's use this particular, what we have learned right now, that next bit unpredictability is sufficient to get pseudorandomness in a very, very toy case, which is that suppose I just want to stretch one bit. I stretch by one bit. That is, I need a stretch of one. What I mean by that is I give you a seed of length d. I am asking you to give me d plus 1 bits that look uniform to somebody else. Okay. I mean, on the face of it, it feels like, why would this even be useful? But this is like a stepping stone. I mean, it's like one of these epsilon steps that you do to prove much, much stronger statements. And there was a really nice idea that Nissan and Wigderson came up with. This is something we will deal with towards the latter part of this module. But I still want to tell you, because to me, it feels like this is the most natural place to tell you about a little bit about what Nissan and Wigderson did, which is they basically said, let's just do the following. What do I want? I want to make sure that the next bit is not predictable. Somebody has already given me d bits. So let's just say the first d bits of whatever I'm outputting is the same x. I mean, I was given uniform, it was not predictable. So of course it is still not predictable, but my job is still to figure out what is the next bit I need to put. I need to put a particular bit here because I'm supposed to return b plus 1 bits. And I want it to be unpredictable. So let's just do the following. So let's just say this b is basically a really hard function applied to x. And the whole point of b is that I don't expect a small circuit to be able to compute this hard function and thereby figure out that this b was actually equal to h of x. Okay, so I mean, it's not just hard to compute, it's actually hard to guess. So they defined, I mean, I don't know if they defined it, but they used the notion of what is called average case hardness, in the sense that it's hard to even guess the value of the function, and said that you can, if you have an average case hard function, you can actually use that to stretch the PRG a little bit. And once you have this idea, they then showed you how you can extend this to actually stretch it by a lot of bits. Okay. And we will see this later in the course, which is that if you have access to what are called really hard functions, I'm being vague here purposefully, because I don't want to go into the details here, then you can actually use this to build really, really good PRGs. Like PRGs not with stretch 1, but something that stretches d bits to something like 2 to the d bits or something, depending on what sort of hardness you have. And the funny thing about it is, now you can ask, what do you mean by hard functions? These are functions that are hard to compute by small circuits. Now, if you step back, if I pick a function at random, that is also hard to compute by small circuits. I mean, just because of the fact that most functions are hard. So even hard functions just in its own right form what are called pseudorandom objects, because it seems to have certain properties of hard functions. Sorry, certain properties of random functions, namely that neither of them are actually computable or even guessable by small circuits. So this is like a slightly different philosophy that often shows up in pseudorandomness, which is that if you can find hay in one haystack, you can use that to find hay in some other haystack, which is that if you know how to build, let's say, hard functions, I will show you how to build pseudorandom generators. And there'll be many applications where the fact that you could find hay in some haystack is super useful in making your search in another haystack better. Like it'll often expanders will suddenly play a role, codes will suddenly play a role. So there's a lot of interplay between these different pseudorandom objects, even though they all feel roughly similar. That you know for a fact that a random object works, you're trying to somehow lay your hands on an explicit one. But somehow this helps a lot.
Ramprasad, this is not Nissan Vigderson. This is Blum Mikali more than 12 years. Nissan Vigderson is how to get several bits.
Yeah, okay. Yeah, sorry, I didn't, okay. Okay, so what will eventually, I mean, I don't know if we'll have time to see a proof of this or something, but this is what we seem to know currently, which is that our definition of a hard function is that suppose there is a function that is computable in exponential time. That's what I mean by t time 2 to the order n, but requires circuits of size, I don't know, 2 power n by a million. Then you actually get an optimal PRG that will let you de-randomize BPP completely. Like it basically tell you that as far as decision problems are concerned, randomness gives you no additional power. And I don't know, to me, this is like such a strong statement in the sense that it's a statement where the hypothesis seems to be a statement about hardness. You're saying that something in exponential time is hard. And that translates to randomized algorithms are easy in the sense that you can somehow make it easier. So it's a strange flip that seems to be happening here as well. Okay.
Okay, I want to mention one more thing. This confusion between Mikali, Nissan Vigderson, and this hardness versus randomness paradigm. Nissan Vigderson are the people who perpetuated this confusion. The paper of Mikali and Mikali's thesis is called Hardness versus Randomness. And Nissan and Vigderson steal that thesis title for their paper title to show this paradigm, continue this paradigm. That is, hardness and randomness can be traded for each other. Yeah. And that's what the idea.
Yeah, so I doubt if we'll be able to see the proof of this, but we might be able to see proof of slightly weaker statements. We'll see it as we get along. But this is typically the setup for general, what do you call it? Pseudorandom generators against BPP or against small circuits, because often the statements we have are they're conditional. Like it's of the form, if something happens, then something else happens. And maybe the hypothesis is something we strongly believe in, but we don't have a proof of those things yet. So there's a lot of statements with respect to things that result in either P equals BPP or BPP has some de-randomizations, which is all conditional on certain kinds of objects existing, which we don't yet know if they exist. But I must say this is primarily the reason why people believe that P equals BPP. The reason a lot of people believe that randomness for decision problems do not give more power is because it seems natural that there will be some problems that are solvable in, I don't know, 2 to the million times n time, which is not solvable in 2 to the n over a billion. I mean, I shouldn't say it's not computable by circuits of size 2 to the n over a billion. It seems like of course that ought to be true, but there are nuances to this, and we are very far from proving something of that sort. But I mean, if that is indeed true, then it turns out that you can actually de-randomize all probabilistic decision problems. Okay, so this is all I wanted to give about the general thing. I also wanted to tell you a little bit about low space algorithms and introduce you to RL, but I think I will do that in the next lecture. But over the next few lectures, what we are going to be focusing on are not just arbitrary efficient algorithms, but we're going to be interested in efficient algorithms that run in small space. And there's a strong connection to just graph reachability and related questions. And these are some instances when we can construct unconditional pseudorandom generators. So that's what we're going to be focusing on in maybe the next 3-4 lectures. And then we might revisit the general circuit setting where we prove some conditional results. Okay, so I'll stop here for now. And this part of the lecture onwards, I mean, I'll do this in the next lecture.
So I have a question.
Yeah.
So in the Chernow bound, where we wanted to prove that there exist pseudorandom generators in abundance. So the only thing we use about circuits is that the circuits of a certain size are not too many.
Yes, that's right. That's precisely right. Yeah.
Right. So we could just replace everything by saying that, okay, you collect so many Boolean functions, then you have a.
That's an excellent point. In fact, this is something that will show up at multiple places, because often when you're trying to figure out what is the right answer to this, it's often good to get a sense of how many things am I fighting against, rather than you don't particularly care about what you are fighting against. It's somehow this number that seems to matter when you're trying to figure out how long can I expect a random construction to work. So as you rightly pointed out, I mean, the key point in this entire thing is just the fact that the number of circuits of a certain size is not too many. So if you replace it by a certain subclass of circuits or certain tests of a certain kind, etc., all of this will work. Like, for example, you could do the following. Suppose I replace this with all sort of parities. Okay, that is a parity on any of these m bits. Well, you could have replaced this with just 2 power m and said that, okay, this much seed length is enough, which again makes sense because that's what we did for epsilon bias spaces. So it is indeed a very general sort of statement.
It's just a counting argument.
Yeah, it's just a counting argument written in a probabilistic manner that exhibits that there are these objects in plenty. It's more like, like most of the time we are sure that these objects exist. We are mostly trying to figure out what is the right parameter choice. And for that, this argument is very helpful. It gives you a sense of what you should aspire to get. Yeah.
But on the other hand, every probability argument on finite objects is a counting argument. But no. Jokes aside, this can also be turned on the other way around. If you know that the number of objects you're trying to fool is very large, you can show that actually you can use it on the other side also. You can show that you can't get seed length smaller than this because there are more objects than you can fool. You can sort of try to make that formal, state that there will at least be one object which escapes being fooled. You can use that to show it. And sometimes we also have lower bounds on seed lengths.
Yeah. So there, I guess there at some point it depends on what these many objects are. But yeah, in many cases you can actually turn this argument around to also give you a lower bound. Yeah.
So I think we already saw that if you just take linear functions, all linear functions on the target, then you cannot fool the uniform. You cannot become too close to the uniform distribution.
That's right. So like in your problem set also, you had a lower bound for epsilon bias spaces to sort of say that even if I tell you that, okay, I allow you to get epsilon close to it, can you do better than log n over or n over epsilon squared?
Yeah.
We saw that you can't do. Okay, maybe there's an extra log 1 over epsilon factor, but something like that. So yeah, so this is a very standard sort of argument to sort of say that you're fighting against this big bag of objects, and at some point there is just what is going to be relevant is how many objects you have, and that will give you a good sense of what you should expect your parameters should be.
Okay.
All right. If there are no further questions, then we will meet on Tuesday. Okay, great. So I stop the stream.